Here is a curve, and here is a single point on it. I want its steepness right here, but steepness is rise over run, and at one single point, there is no run to speak of. So how can one point have a slope at all? Watch. Start with something we can measure. Pick a second point, a little further along. Between the two, the curve has an average steepness, the change in height divided by the change in a cross, rise over run, which is just the slope of the straight line joining them. That joining line has a name, the secant. Now the move that unlocks everything. Slide that second point inward, closer and closer to the first. The gap between them, call it h, shrinks towards 0. Keep your eye on the secant and on its slope on the left. As h closes to 0, the secant pivots and settles onto one single line, a line that grazes the curve at just this point. That limiting line is the tangent, and its slope, 2, is the exact steepness we were after. A secant pushed to its limit becomes a tangent. Put that in symbols, and you have the derivative. The slope of the tangent at x is the limit, as h goes to 0, of f of x plus h minus f of x all over h. This is the derivative from first principles, the very definition. And read the small print carefully. H approaches 0, but it never equals 0. If you set h to 0 outright, you get 0 over 0, which tells you nothing. The whole art is to simplify first and take the limit last. Let's run it on the simplest curve. f of x equals x squared. Form the quotient. f of x plus h is x plus h, all squared over h minus the x squared. Expand the bracket. X plus h squared is x squared plus 2xh plus h squared. Now the x squared and minus x squared cancel, leaving 2xh plus h squared on top. Every term has an h, so divide through by h. That gives 2x plus h. And finally, take the limit as h goes to 0. The lone h vanishes, and the derivative of x squared is 2x. Notice we simplified first. Then let h go. Never 0 over 0. So the slope of x, squared at any point, is 2x. And that is itself a function, the gradient function. Here's what that looks like. As a point rides along the curve, its tangent tilts, and a second point marks the slope at each spot. Now watch the trail that second point leaves. As it sweeps across, the slope it records draws out a perfectly straight line. The line 2x. The derivative of a curve isn't a single number. It's a whole new function that gives the slope everywhere at once. Two things to carry with you. First, h approaches 0, but never equals it. So simplify the fraction first and take the limit last. Set h to 0 too early, and you get 0 over 0, which says nothing. Second, a derivative is a slope at a single point, which means it is a function, not one fixed number. All prime of x hands you the slope everywhere at once. Hold those two, and first principles is yours. So a derivative is a slope at a single point, the limit of a secant as the gap closes. And it is itself a function, the gradient function. That one idea powers everything ahead: rates of change, tangents, maxima and minima, motion. Next, the shortcut rules that let you differentiate without doing this limit every time. For more, that's MarkScheme.app.